Good afternoon. Welcome to week 10 of the course Applied Optics by NPTEL. This week we have been introduced to the concept of birefringence and other effects related to polarization. For example, the Malus law and the Brewster's angle. So all these concepts are pertaining to the polarization of light, and in this week the assignment problems would also be dealing with polarization of light. Before proceeding, let me put up the link to the YouTube channel of the course in the Zoom chat box. This YouTube channel is where you will find the recordings of all the previous problem solving sessions as well as the live stream of this current session. So let us get started. The first question over here is on Brewster's angle. A light ray goes from air with refractive index n equal to 1 to glass with refractive index n equal to 2.23. Brewster angle for this ray will be, we need to calculate the Brewster's angle. So I will start the poll for you. Please take a few minutes to calculate this and submit your answer in the poll. Let us now discuss the answer. So what we have is an interface, air to glass interface. So let me first draw the interface. So this is the interface, and then we have a ray coming in we have a ray coming in, then we will have a normal to this ray, and then we will have a reflected ray as well as a refracted ray. This is the reflected ray, and this is the refracted ray, and these are the refractive indices N1 and N2 of the medium. Now, if this incident ray is at the Brewster's angle theta p, then something interesting happens. And what happens? Let us see. So if we have an incoming unpolarized beam, that means it has polarizations varying randomly in all directions, and the nomenclature is that this dot represents polarization perpendicular to the plane of incidence, and this line represents polarization parallel to the plane of incidence. And the plane of incidence is the plane containing the normal, and the incident ray. So that's the nomenclature. And if it is at this particular angle, then your reflected ray is completely polarized, and the polarization of the reflected ray is perpendicular to the plane of incidence. So perpendicular means it is coming out of the plane of this screen, and the refracted ray is partially polarized. And also, the angle between the reflected and the refracted rays is 90 degrees. So Brewster's law states that this angle theta p at which this interesting phenomenon happens is tan inverse of N2 over N1. Now, how does this come from? We can see that the reflection coefficient for the parallel component of the polarization is given as follows, where theta I is the incident angle and theta r is the refracted angle. Now this reflection coefficient for the parallel component is 0 only when my theta I plus theta r is pi by 2. Why? Because tan of pi by 2 is infinity and 1 over infinity is 0. So why this is there? Because tan pi by 2 tends to infinity and 1 over infinity tends to 0. So this means that for Brewster's angle, theta I is theta p, the Brewster's angle, the reflected and the transmitted or the refracted rays make an angle pi by 2, which is 90 degrees. And from Snell's law, making use of the Snell's law, we have N1 sine theta of the incident ray, that is theta p, is N2 sine theta of the refracted ray, that is theta r. So this gives us N2 sine pi by 2 minus theta p, because sine theta r, so theta r is pi by 2 minus theta p. Okay, so let me first write the left hand side. Now sine pi minus theta is cos theta. So this gives me tan theta p equals n2 over n1, from which we get the Brewster's law that theta p is tan inverse n2 over n1. So for our case, theta p, the Brewster angle that we are supposed to find, is tan inverse n2, which is the glass refractive index, which is 2.23, divided over 1, which is the air refractive index. And this comes out to be roughly 65.85, just putting it in the calculator. So option B is the correct option. Moving on to the next question. The correct statement for a birefringent medium is what we need to find out. We need to select, and these are the 4 options. So we need to select the correct statement for the birefringent medium. I will refresh and restart the poll. Let us now discuss the answer. The correct option is A. Ordinary ray follows Snell's law. Now, let me just briefly introduce the concept of birefringence to you. So, we have a birefringent crystal, typically calcite is one such crystal. And when you send in an input ray to this crystal, then you have it getting split into two rays. So if the input ray is unpolarized, then we have these two rays. One is the O ray, which is the ordinary ray, and one is the E ray, which is the extraordinary ray. And the O ray has one particular polarization, which is perpendicular, and E ray has the other polarization, which is parallel. So you can basically use birefringent crystals to obtain polarized light from unpolarized light. And we have the speeds for the ordinary and extraordinary rays given as follows. So the ordinary ray is the usual that we know. So the speed is c over n, and O being the refractive index for the ordinary ray. Whereas for the extraordinary ray, it is a bit non-trivial. And we have the following relation. Where theta is the angle between the E ray and the optic axis. And if this angle is 0, if theta equals 0, then the ordinary and extraordinary rays have the same velocity. That means along the optic axis, both the E ray and the O ray will have the same speed. So we can now move further. Let me check if there is any question. Okay, so there is one question. Okay, yes. So the extraordinary ray does not follow Snell's law. E ray does not follow Snell's law. Snell's law is applicable only for the ordinary ray. And up until now, we were not dealing with birefringent crystals. So as a result, the ray was ordinary ray and it followed Snell's law. Question number 3 now. Unpolarized light of intensity I naught passes through a linear polarizer with transmission axis oriented at 60 degrees relative to the horizontal, then we need to find the intensity of the transmitted light. After the polarizer. And we have 4 options. I will refresh and relaunch the poll. Please take a few minutes to answer. I see some people are putting their answers in the Zoom chat box. I would request that all of you please use the poll and please select the correct option in the poll itself. the correct answer to this question is I naught by 2, option B. And this comes from Malus law. So Malus law states that the output intensity after a polarizer is I naught, which is the input intensity, times cos squared theta, where theta is the angle between the linear polarizer axis, the linear polarizer transmission axis, and the polarized light polarization. Polarization direction. Now when you have unpolarized light, our input is unpolarized, so for unpolarized light it will be the average of all the angles, because in unpolarized light the polarization angle varies randomly. So since it varies randomly, we need to take average of all possible angles from 0 to 2 pi, and average of cos squared theta is half, and thus we get I naught by 2. Now how do we get this average of cos squared theta? It's pretty simple. So you need to integrate from 0 to 2 pi, so this gives me 1 over 2 pi. This 2 pi is integral d theta, and integral 0 to 2 pi of cos squared theta d theta. Now from trigonometric identities, we know that cos squared theta is nothing but 1 plus cos 2 theta over 2, and cos 2 theta integrates out to 0. So the only contributor to the integral will be by this 1 by 2 term. And so from 1 by 2 you get 1 by 2, and integral of d theta again 2 pi, so this gives you 1 over 2, and that's how you get the output intensity is I naught by 2. So when you send in unpolarized light, then no matter what is the orientation of the transmission axis of the polarizer, the output intensity will always be I naught by 2. Okay, so we can now proceed further. Question 4, it's a straightforward factual type question. A polarized light beam cannot be produced by option A, scattering, option B, reflection at Brewster angle, option C, double refraction, or option D, interference. The correct option is option D, interference. We can create polarized light through scattering, through reflection at Brewster angle, and by double refraction. We already saw these examples of reflection at Brewster. Okay, sorry, I should have written angle. So we already saw these examples earlier in the earlier questions, how reflection at Brewster angle and double refraction creates polarized light. Let us just revisit once again. So this is Brewster's law, and if we are incident at the Brewster angle, then the reflected light, this light is polarized. So reflection at Brewster angle creates polarized light. Same way with the double refraction. This is phenomenon of double refraction. It splits the incoming unpolarized light into two polarized beams, the ordinary ray and the extraordinary ray, both of which are polarized. But interference cannot generate polarized light. The next question. X polarized light of intensity I naught passes through linear polarizer with transmission axis oriented at 60 degrees relative to the x-axis. The intensity of transmitted light is option A 0, option B I naught by 2, option C I naught by 4, and option D 3 I naught by 4. So this is based on Malus law again, which we discussed earlier. I have restarted the poll. Please take a few minutes to answer. Let us now discuss the answer. So first we need to review Malus law. So we had discussed it in one of the previous questions. We will discuss it again. So Malus law states that the output intensity after a linear polarizer is I naught, which is input intensity, times cos squared theta, where theta is the angle between the polarizer's transmission axis and the input polarization direction. So in our case, we are given that the polarization of the input light is along the x-axis and the transmission axis, so input light is x polarized and the transmission axis angle is 60 degrees with respect to x-axis. So angle between the polarization direction and the transmission axis in our case is 60 degrees. Thus, the output intensity would be I naught cos squared 60 degrees, and cos 60 degrees is half, so we get I naught by 4. Correct option is option C. So I hope by now Malus law is clear to all of you, Malus law and Brewster's law. If not, please feel free to ask in the chat box. Okay, so I think we can proceed further. Question number 6. An unpolarized light beam is launched at Brewster angle at an interface between two media. In this situation, the refracted light will be what we need to select from the options. Take about a few minutes to answer this. Okay, so let us discuss the answer. The correct option is option B, polarized perpendicular to plane of incidence. Sorry. So let us once again review Brewster's angle, which we saw in the first question. So this is the interface, and let's say we have in an input ray, then we will draw the normal to this input ray. And then the reflected ray and the transmitted or the refracted ray. And at the interface, this is refractive index n1, this is refractive index n2. And when we send in unpolarized light, and if this incident angle is the Brewster's angle theta p, then the reflected light is polarized and the refracted light is partially polarized. And also the refracted light and the reflected light make an angle 90 degrees with each other. And the nomenclature is that this dot represents polarization perpendicular to the plane of incidence, line represents polarization parallel to the plane of incidence. And just to state the Brewster's law again, the angle theta p is given as tan inverse n2 over n1, and theta p plus theta r, this is theta r, is 90 degrees. Okay, so that is about Brewster's law. Moving to the next question. This is also on Brewster's law. An unpolarized light beam is launched at Brewster angle at an interface between two media. In this situation, sorry, I did a mistake over here. This is not refracted light, this should be reflected light. I'm really sorry about that. Let me correct myself once again. The previous question was for reflected light, this question is for refracted light. So in the previous question, it was about reflected light. We were sending an unpolarized light beam at Brewster's angle at an interface, and then we were looking at the reflected light. Reflected light meaning this particular light beam. This is the reflected light. So the reflected light is polarized perpendicular to the plane of incidence. So thank you for pointing it out. Someone had pointed it out in the chat box. Yes, so indeed I made a mistake in writing the question. So for the reflected light, the beam is polarized perpendicular to plane of incidence when the incident beam is unpolarized and incident at the Brewster angle. So I hope I have made myself clear. Sorry for this mistake. Let me repeat. If we send in unpolarized light beam at an interface between two media at the Brewster angle, where Brewster angle is the angle of incidence, then in this case the reflected light will be completely polarized and the polarization direction would be perpendicular to the plane of incidence. And the plane of incidence is the plane containing the incident ray and the normal to the interface. I hope this is clear now. Sorry for the confusion. Coming back to this question, this question is on refracted light. Again, similar question as previously it was about reflected light, now it is about refracted light. Please take a few minutes to answer. let us now discuss the answer. So this question is similar to the previous one, so let me just copy paste the stuff from there. Okay, so just copy pasted the stuff. Now we are not looking at the reflected light, now we are looking at the refracted light. So this is the refracted light. Now what we can do is, even in refraction we can create nearly polarized light beam. And how do we do that? We do that by adding multiple interfaces. So what we will do is, we will have many interfaces. And let us send in a light beam on the first interface such that it is at the Brewster angle, and this input light is unpolarized. Because of Brewster angle, the reflected light is polarized. And then we have a refracted light. This is the refracted light. Again, this and this refracted light is partially polarized. And again, this is incident at the Brewster angle for the second interface. And then we have a reflected light which is completely polarized, and then a refracted light beam. My diagram is looking little bit not so nice, but you kind of forgive me for this kind of drawing skills. And again, the refracted ray will be partially polarized, but the degree of polarization this time will be higher, because we are continuously filtering out the perpendicular component. again we filter out the perpendicular component. So the transmitted ray would be having greater degree of polarization. This is 90. Once again we filter out the perpendicular polarization. And we have refracted light, then reflection, and then finally we will have light beam which comes out. And this light beam would be very nearly polarized. So this way we can increase the degree of polarization. And that's how even in the refracted beam we can get very high degree of polarization, with the polarization being parallel to the plane of incidence. Moving on to the next question. At Brewster angle, the relation between incidence angle and refraction angle is option A, theta I plus theta R equals 180 degrees. Option B, theta I plus theta R greater than 90 degrees. Option C, theta I plus theta R less than 90 degrees. Or option D, theta I plus theta R equals 90 degrees. Okay, so I will not discuss the answer first. First, you people attempt this question, then we will discuss the answer. Okay, so let us now discuss the answer. So as we have seen many times in this assignment, Brewster's law states that theta p is tan inverse n2 over n1. This is the Brewster's angle. At this angle, the reflected beam is completely polarized with polarization perpendicular to plane of incidence. So the parallel component has zero reflection. So the reflection coefficient for the parallel component is given as follows. This is the incident angle. Now this is 0 for when we are at the Brewster angle. And this will be 0 only for theta I plus theta r equals pi by 2. Why? Because when theta I plus theta r is pi by 2, tan pi by 2 tends to infinity and 1 over infinity tends to 0. So the parallel component has 0 reflection, which is the situation for Brewster's angle. So theta I plus theta r is equal to 90 degrees. Option D is the correct option. Okay, next question. Question 9. A circularly polarized light of intensity I naught is passed through a polarizer if polarizer is rotated with angular frequency omega, then the intensity of transmitted light is what we need to find. Okay, so these are the 4 options. Take about a minute to answer. Okay, so the correct answer is option C. It remains the same on rotation, and the intensity in fact will be I naught over 2. Now this, if you recall, you might think this looks similar to unpolarized light, and the difference between circularly polarized light and unpolarized light when it passes through a polarizer is as follows. So in circularly polarized light, the polarization of the light changes like in a circular motion. It rotates along this circle with uniform angular velocity. So the orientation varies with time. And the difference is that this is predictable. This variation with time is predictable. If I know what is the orientation at t equal to 0, then at t equal to t, I can predict the orientation based on the angular velocity. However, for unpolarized light, the orientation is unpredictable. So it will not go nicely and uniformly around the circle. At one instant it could be horizontal, next instant it could be vertical, third instant it could be over here, fourth instant it could be over here, then fifth time here, sixth time here. Like this, it could just completely be random, unpredictable. So if you know the orientation at t equal to 0, you cannot predict the orientation at some time t equals to t. So that's the difference between circularly polarized light and unpolarized light. But in both the cases, when you pass it through a linear polarizer, because the orientation is changing with time, the output intensity would be I naught by 2, and it would not change with the orientation of the polarizer. And this we saw earlier was because of this average of cos squared theta coming out to be equal to half. So this is also true for circularly polarized light. Okay. Finally, the last question of the day. This is on birefringent crystals. In a uniaxial crystal, ordinary and extraordinary rays have the same speed along option A, one direction, option B, two directions, option C, all directions, and option D, none of these. So let me relaunch and restart the poll one last time for today. Please take a few minutes to answer. So the correct answer is option A, one direction. And this particular direction is known as the optic axis, wherein both the rays have same speed. So if we write down the speeds for both the rays, so for ordinary ray, speed is this, VO is C over NO. This is the usual that we know. For extraordinary ray, it's a bit complicated. Where theta is the angle between E ray and optic axis. And clearly you can see that when theta equals 0, we have VO equals VE, which is C over NO. And if two directions have the same speed, then that is the case for a biaxial crystal, which has two such axes where the ordinary and extraordinary rays have the same speed. So this brings us to the end of week 10. We have 2 more weeks to go for this course. This is 12 weeks course. So next week we will discuss week 11 assignment problems next Saturday at 3 p.m. Okay, see you. Bye bye. If you do not have any questions, please log out from this Zoom meeting. Else you could post your questions in the chat box. Okay, bye everyone. See you next week.